the results. All the questions are multiple choice or true false, and it'll be automatically graded, so the grades will be available quite soon. So you have from Thursday at 11, all the rest of Thursday, Friday, Saturday, Sunday, and all of Monday to do the exam. As promised, it's completely open, everything except each other, except any humans that you can't ask, you can't consult any humans. But other than that, you can go to the web, you can go to books, you can go to your notes, you can go to anything other than other humans. And you must pledge that you will not have gone to other humans during the time you were taking the exam. Okay? I count in the exam that there are 81 answers. Okay? That is, so you'll be graded out of something out of 81. I think I've counted right. But anyway, one true-false answer is counted as one answer, right? One multiple-choice answer is one answer. It covers the ground that we've covered, and I'll show you. We'll go through the sample exam now. I am here to answer questions now, at the end of class, or in my office hour today, which is 2:30 to 3:30. I have a commitment from 3:30 to 4:30, but if any of you tell me either now in class or during the 2:30 to 3:30 hour that you need more of me, I will be available again at 4:30. But I will not stay around if nobody's told me that they're going to be coming. Any questions about that? I apologize for having not graded assignments before now. I decided to grade assignment 6, which was going to be the most challenging first. I'm in the middle of doing 3 now, and I'll have 3 and probably all of 4 done by the end of today. With regard to assignment 6, the first problem is that some of you submitted your reports in unfortunate formats that I couldn't easily grade. Please submit assignment reports as PDFs. Many of you did very, very well on assignment 6, and I was pleased to see that. But also many of you missed submitting certain parts. And I obviously couldn't give credit for that. I searched with the help of one of my LAs for all the parts that I was looking for, and I reported back to you in the reports that I believe the Sakai grading system will. Each of you should have gotten a report. One of you submitted via email rather than that, and I did grade that one. Anyway, if you don't know what your grade is or don't understand why your grade was what it was, I'm happy to have you ask me questions. If there was a part that was reported as missing and it really wasn't missing, come show me. Moreover, that assignment, was very instructional. And even if you didn't do some parts, if you did them now, you could still get 50% credit. I'm not I mean, credit is not what the assignments are for. The assignments are for making the lecture material concrete. They're for learning purposes. They're for educational purposes. The credit business, well, I know you're all concerned with getting appropriate credit. It is a spur for you to get that part of the education, if you will. But anyway, there's still 50% of it worth. And the assignments, I mean, typically what happens in this course, I mean, some of you will do, very, very well on everything. But on average, the grades in this course are higher on the assignments than on the exams. And there's a significant credit in the final grade on the assignments. And so, getting a good grade is aided by getting adequate numbers of points on the assignments. Okay, anyway, please feel free to question something that I did, show me something that I didn't see, or to submit a late part. In assignment number 6, you were asked to yeah, it's a question?
Yeah. So if we didn't, if we submitted the report in another way besides the PDF, would you like us to resubmit that as PDF now?
Yeah, I mean, if something was taken off because I didn't see a report,
okay,
then submit a report and you get partial credit. In the Eigencars results, those of you who, almost all of you, got rather reasonable results. Some of them were worse than there was something bad enough that I didn't believe that you were doing quite the right thing in your computation. But nevertheless, all of you who got sort of reasonable results saw that the Eigencars approximation looked like a car. It might have been a slightly noisy car or a slightly, blurry car or whatever, but it looked like a car. And I asked you to do the sinusoids with the same number of eigenimages, the same number of basis images. And you saw that it didn't look like much it looked like a big blur. It didn't look like a car at all. And yet, you may have noticed that the RMS error was comparable between the really ridiculous sinusoid result, didn't look like a car, and the Eigencars one that did, okay? In fact, for some of the examples that some of you used, the RMS error was actually lower for the sinusoids, although for most of you, it was a bit lower for the Eigencars expansion. But never mind, the point that I'm trying to make here is that RMS error is clearly not a very good measure of the quality of an image. From our point of view, the kinds of things that we look at in an image focus on the objects and especially on the edges of the objects, right? Human vision does that, and computer vision focuses on those as well. Image analysis, whether they be of medical images or of images from regular light cameras. Anyway, the point is, it was worth me noting now something that I hope you noticed. You didn't have to say it in the exam, but some of you did, and I'm glad you did. That the quality of the Eigencars quality was much, much better from a visual point of view, even though its RMS error wasn't all that distinctive. Yeah, I want you to be careful with image display. In any display system, you can't depend on exactly what it's doing. When you display an image, if it has negative values, for example, MATLAB doesn't know what to do. It doesn't do the right thing. If, in general, it's good practice when you're doing a display to rescale. If you have the minimum image intensity as A and the maximum image intensity as B, that is to say, all the image intensities in something you want to display goes from A to B. If you take any pixel and subtract the minimum and divide it by the range, and then multiply by however many intensity values you expect the display system to provide, I think in MATLAB it is 256, you will get a more comparable display between different results. All the more so if A happens to be negative. Some of you in assignment 4, the edge assignment, where I am in the middle of grading right now, got some displayed results and you were doing comparisons based on the display, which were valid if you simply displayed without this rescaling of the intensities. But weren't necessarily the appropriate conclusion. I didn't take off credit for that, but you should be aware that you need to be careful when you do displays and then make decisions based on the displayed image. What have I left off here? No, nothing that I can think of. Questions before I finish? We now do finish the summary before the midterm.
Yeah, someone in Zoom asked if we're going to have class on Thursday.
What?
Someone in Zoom asked if we're going to have class on Thursday.
Yeah, Thursday there's a class. Certainly, yes, class. There is a class on Thursday. The exam is not using any class time. It's take-home. Yeah.
I just want to make sure I understand. That range is going to be the intensity of overall pixels, right?
Yeah. A is. A is the minimum over the whole image of all the intensities in the image. And it's just two MATLAB commands, the min and the max. You get your A and your B, and then you. Is that clear? Okay, I'm going to go on with the lecture then. The last part of the how do we get rid of? Okay, so this is the last of the summary slides that I didn't get to cover last time in my summary. And so we had a part of the lecture material on locality and scale before the material was closed. And I want to just make a summary of that. The first point was that if you have an image, all the operators we studied up to that point were global. They applied to the whole image, and every coefficient of an eigenimage of a basis image depended on all the pixels. You changed any pixel, and you changed all the coefficients. And that does not allow you to appropriately focus on a particular part of the image. And that turns out to be harmful from the point of view of getting image properties that are relevant to us, to make measurements on the image. And so we need this idea of being able to focus on a particular part of the image. And we do that using an aperture. Okay? And there are computationally, from the point of speed, advantageous apertures. Certainly the rect function, for example. All you have to do is add up all the intensities in that part of the image, right? If you have an image and you put down a rect function somewhere, then all you're doing is adding up all the intensities under that box. And that's fast. But from an effectiveness point of view, as opposed to a computational speed point of view, we saw that the Gaussian was very much preferred over any other aperture. And we saw that when you talked about scale, there needed to be two different properties that we considered. One of them was the aperture width, which in the case of the Gaussian could be measured by its RMS width, which was the sigma of the Gaussian. But there was another one called level of detail. And depending on the particular way of producing results in a locality, there were different ways of producing different levels of detail. In the case of one of the possibilities, which was to understand the basis images as Gaussian derivatives, you have some very nice interpretations of that, but they're not orthogonal. Nevertheless, they're calculated pretty efficiently by going into the frequency domain. But when you do that, essentially the distances between relative maxima of derivative of a Gaussian are what you can think of as a level of detail. Or you can take distances between, you say the half level of detail, the difference between a max and a min. So for the second derivative, it would be the level of detail would be roughly the distance between this peak and that value, right? For a first derivative, it's the distance between twice the distance between this peak and that pit. Okay, you understand that I think you can see that as you have higher and higher derivatives, you get more maximum and minimum. In fact, you just increase the number of, you have one maximum for the zeroth derivative, a max and a min, two extrema for the first derivative, 3 for the third derivative. You can figure out what's going to happen for higher order derivatives, right? Okay, so Gaussian derivatives, the relative, the position between their extrema can be thought of as the half wavelength, as the level of detail. For Gabor wavelets, you have a Gaussian aperture, but you have a sinusoid underneath it. And it's the wavelength distance between successive maxima, or you can take the difference between a maximum and multiply it by 2, that you can talk about as the level of detail for that one. We noted that you had the orthogonal wavelets, which were not produced by Gaussians, but which had very nice property, computational property, of producing orthogonal basis images, and which were, I'm not going to say Gaussian-ish. That is to say, they had the aperture had a single maximum, and the envelope fell roughly by the same rate as for a Gaussian. And the level of detail for that one was specifically proportional to the aperture size. So as you scrunched the aperture, you correspondingly scrunched the level of detail. Not a topic on this exam, but a topic for us as we go on, is that this general property of having a level of detail proportional to the aperture size is a good thing. It turns out to be a beneficial way of producing things. But nevertheless, the notion of level of detail and aperture size are two separate things that you need to understand. Any questions?
I have one question.
Go ahead.
When would the Gabor wavelets, when would they be preferable over like Gaussian derivatives?
Depends on your religion. If you ask Harry Wexler, he'll tell you most of the time, and if you ask Dr. Haromani, he'll tell you almost never.
Or I guess what's the major difference? Like
I mean,
very
the point
similar.
is the measurements you get out of these things come from the coefficients of the basis functions. Okay, you're trying to find edges, or you're trying to find objects, or you're trying to find bars or other things in images, circular blobs, whatever you might be looking for in images. The two methods give roughly the same kind of results. There's not a major advantage in my experience for the two of them. So it comes down to, on the one hand, computational speed issues, or other kind of mathematics that you want to think about doing. I mean, so if you want to understand, if for some reason or another the fourth derivative properties are especially interesting to you, then you probably should go for, the fourth derivative one, because that one, or if you're trying to expand things in some kind of a Taylor series or some kind of a polynomial like that, yeah, that's going to be beneficial. If, on the other hand, thinking of things in terms of frequencies is particularly if you have an object that somehow has a regular repetitious, truly cyclic property, then Gabor wavelets. And so the place that you see Gabor wavelets used most frequently is in understanding textures, because I don't know, the texture of an image I take of the class is going to be related to the spacing between all of your different seats, right? And generally speaking, textures have this, at least locally, truly cyclic property. That is to say, every cycle is the same as another cycle. And when cycles are important, then you want to think in terms of cycles. And then that's why the Gabor wavelets are used very frequently for texture measurements. So it really depends on what your objective is specifically. Now, in other cases, the texture is not close to cyclic. I mean, so you have, if I have my hand, the texture for my fingers, these two are spaced about a certain amount apart, and these may be a little bit different. And from here to here, from my ring finger to my small finger, I have a much bigger distance, so it's truly not cyclic, right? And then something that depends on being truly cyclic is not the right way to go. And people have struggled to come up with comparable texture measurements to the ones given by the Gabor wavelets when the cyclic assumption is not so, right? And yeah, there are some interesting papers on that. Okay, but that sort of depends on quite what you're after. We also saw the splines, and the main point about the splines were that they're patchwise, and for each patch, and the patches are smooth in an engineering sense. Okay, so when a mathematician says smooth, they mean continuous in every derivative. And those mathematicians can go ahead and make that decision, but we engineers are happy if it's smooth, if it's continuous in zeros, first and second derivatives. And so we call those smooth. And so you get patches. The image is divided into these patches, and they're smooth on the boundary of the patches, and associated with every patch there is an area where the control values are used, and so they're truly local, which is typically larger than the size of the patch. In the case of the B-splines, it looked like what I just drew. The exam will not cover the details of the Gabor wavelets or the orthogonal wavelets or the splines, but understanding as much as I just said is covered. Okay, all this business about how the control points and the polynomials and all that kind of stuff is not on this exam, but understanding patches and apertures is. Any questions on this review of the part that's going to be covered on the exam? If not, let me go through the practice exam. Okay. So, I don't have the solutions there.
The solutions are just bold.
What solution? Oh, I see. Yeah, it is there. The E is bold. Thank you. Okay, so why is 81 the right answer to fourth derivative tensor size? Yeah,
Well, if you're gonna take four derivatives, each time you have three possibilities with the image. Actually, I got that wrong. Well, yeah, you have three possibilities, three directions. So you do three.
no,
times
for
three
fourth
directions.
derivative, you have four directions. I mean, you have, sorry, you have three spatial, you're right, there's three spatial directions. Better be careful when you put an adjective in front of the word directions. There are three spatial directions, that's right.
So then you do three times three times three times three, which is 81.
That's right. If the order of the derivative, the size of the tensor is 3 by 3 by 3 by 3. The order is 4. And the dimension of the space is 3. And the number of entries is the ordered power of the number of spatial dimensions, 3 to the 4th. Okay? Any questions? Okay, I'm going to stop asking any questions. You're going to say questions if you have them. Okay. If you have a second derivative, first in the u direction and then in the v direction, how can you compute that? And because of the symmetry of the derivative tensor, where the order of the indices doesn't matter, you can take the tensor, or you can take its transpose, and you get the same result. So it doesn't matter whether I have it super T or not super T on the tensor. And the main point is that you need, and it doesn't matter in which order you apply the derivatives, but you basically need to apply one on the left and one on the right here, at least. And the one on the right doesn't need a transpose, and the one on the left does. Ones on the left do. And all of these are okay as a result. Okay, a Taylor series is a linear combination of basis polynomial images. That is to say, a polynomial evaluated at each pixel position. So Taylor series A is true. C, for a 2D image, you need 1/0th derivative, 2 second derivatives, 1 in x and 1 in y, and 4 third derivatives, the xx, the xy, the yx, and the yi. And so indeed there are 7 basis images, although, of course, 2 of them, the xy and the yx, are the same as each other. Taylor series do involve derivatives all at the same point, which makes them extremely local. And whenever you have any derivative of a particular order, it's divided by the same factorial. If you have a derivative of the kth order, you're dividing by k factorial. But the first few terms are not useful as a global approximation because the Taylor series is very, very local. I've said local is good, but the Taylor series is sort of too local. A Taylor series based on a Gaussian aperture is better, and that's what we call Gaussian derivatives. Understanding images in terms of their pixels is what the delta images provide you. Eigenimages allow the computations to be produced by dot products and therefore rather fast. Eigenimages of example images is what we discussed, the SVD approach to get a most economical representation in terms of how many images you need before you can stop listing the coefficients. In general, the number of basis images and thus the number of coefficients for a full exact approximation of an image is the same as the number of pixels or voxels. But if you want to get away with way fewer than those, you will get a lossy approximation, but a good approximation with very few, as long as the training images are representative. Okay, what's not a linear operator on an image? Well, convolution is, by definition, a shift invariant linear operator, whatever the kernel, and thus linear. The diffusion equation was a way to apply Gaussian convolution, and therefore it's clearly linear. There's other reasons you can argue for why, but that's one. A volcano filter is the filter I talked about in the frequency domain. The filter is in the frequency domain, where you're starting to compensate for fall off for a while, and then it falls off. And if you rotate this around that way, you get what looks like a volcano. That's what I call the volcano filter. Okay. If you take two images and some of them have negative values and you set all those to 0, and then you take another image and you set all those to 0, and then you add the result, you will not get the same as if you'd added them, because now some of the ones that were negative are going to be compensated for even something that's more positive in the other image, and therefore you will not have set to 0 one that you would have set to 0 in the other case. So that's clearly not linear, the sum of two images. The sum of two images whose negative values have been set to 0 is not the same as the setting to 0, the sum result. Yeah.
For number 4, what is B referring to?
What is what?
Letter
E?
Eigenimages of a linear
Oh, B.
operator. How is that different? Like C?
Okay, so in the case, you have an operator on an image. You put in an image in and you get an image out, and C turns the input into the output. An eigenimage is something that when you apply C to it, you get simply a multiple of that. Okay? The if the psi are n by n, they're images in 2D, or n by n by n in 3D. Of course, we haven't in this course spent much time on like n by n by m, but that works too. But the point is, these are images. In the other case, we're taking eigenimages of A transpose A. And A point A is n squared by n squared. Well, yeah. Right? So it's completely different completely different these are things that produce an output from an input, the C, and these are collections of sample images, not even close to the same size. Does that answer your question?
Thank
Mm-hmm. Where was I? 6. This one requires you to understand what invariance is. Magnification by alpha, its inverse is magnification by 1 over alpha, right? If you stretch everything in space by alpha, then you compress everything by 1 over alpha, you've done nothing if you've done first one, then the other. And so it's not negative, it's reciprocal. C was all that will expressed here. But anyway, the result of magnification and then demagnification, if you apply an operator to either the original image or to the magnified image and then demagnify it, you get the same result. Okay. So this was, we had two definitions that were equivalent of invariance. One says if you have a geometric operator G and some other operator T, then T is G invariant. If you can do T and then G, or G and then T. The order of the geometric transformation, like magnification, or like translation, or like rotation. There are others, but those are the three we studied. Doesn't matter in which order you do them. And you can multiply this by G inverse, and you get GT, G inverse equals T. That's the same statement, just rewritten in a slightly different mathematical form. And that's what C said. You can magnify and then demagnify. Okay? after with the operator applied in the middle. Okay, so for shift invariant linear operators, you have these funny eigenimages that can be understood as a sine component and a cosine component at a given frequency, or can be understood as a real part and an imaginary part, the coefficients of each, or can be understood, what was the third one? As a phase shift and a magnification. Always two coefficients, two values per eigenimage understood as in one of those three ways for a particular frequency. And so the two real coefficients would be the sine coefficient and the cosine coefficient. The coefficient of the sine the sine basis image and the cosine basis image. Or it would be the real part and the imaginary part in a complex representation. So A is true. The magnitude phase says you have a magnitude, which is real, and a phase, which is an angle. So that's B. The basis images are a sine image and a cosine image for a given frequency. So C is so D. The eigenimages are separable in the case of Fourier approximation, sinusoidal approximation. So you always have an x frequency and a y frequency. And so that's also true. And it's not useful for nonlinear operators. It was specifically for shift invariant linear operators. Okay, on we go. Okay, so when you have an image, the point is the neighbor relations, things that depend on the neighbor relations, such as derivatives, depend on not only what's next to you in a row, but what's next to you in a column or diagonally or what have you. And those aren't easily understood once you spread things out in one vector, because then you have to go from the ith position of one of the position to a jth position, where j is not very much different from I of another sub part of the image. It's just not straightforward to do that. But from the point of view of straight old anything that has to do with the linearity of the operator that's applied, right, such as eigenanalysis, can be understood perfectly well in terms of the spread out parts. So the operations we want to do for analysis are not particularly well explained. But dot products don't depend on you know, what pixel, it's just pixel by pixel. You're just taking the ith pixel of one image and multiplying by the ith pixel of the other one and summing the products. And so that one is a straight vector property. Images are vectors, but they're not only vectors, in other words. Any questions on question 8? Okay, this depends on Parseval's theorem. Parseval's theorem says if you have a set of orthonormal basis vectors, basis images, because images are vectors, you get expansion in terms of that orthonormal set. The sum of the squares of the coefficients are the same no matter what your basis images are. So all of these are, A, B, C, and D are all orthonormal basis sets. And so they all have the same sum of squares coefficients when you expand in terms of them. On to question 10. The idea of compression is to minimize the error when you take only a relatively small number of terms, basis images, and only represent those coefficients. Now, I remind you that what that method did, the SVD method, was to minimize the average RMS error. Right? We just learned that that's a crummy thing to optimize since you saw the result here. Although, it turns out it works pretty well, as I should have seen from the eigenimages assignment, at least the way it was set up. We gave you images that were normalized in intensity and that were normalized in position. That is to say, all the cars were in the same section of the image. If you tried this on images that were not normalized in intensity, it would have done worse. If you tried it where the car was sometimes here and sometimes there in the image, it would have done notably worse. Okay, so you got to be careful for when it's well done. But the basis images are the eigenimages of A transpose A. A way of computing them is to find the eigenimages of AA transpose, the eigenvectors of AA transpose, and then multiply that by A transpose to turn them into eigenimages of A transpose A. But the eigenimages of A transpose themselves are not, they're not even the right size to be images, to be basis images. The eigenvalues in SVD are all squares. They're all non-negative as a result. And you want the theorem says that you use the eigenimages with the largest eigenvalues to minimize your approximation error. SVD. The eigenvectors are not the same, they're not even the same size. But it is indeed the case that they have the same number of non-zero eigenvalues. just the bigger one of A transpose A and A transpose has a lot more zeros, eigenvalues. But A transpose A, as I said, can only have positive eigenvalues. They're all squares. And you can derive the eigenvalues of A transpose from the eigenvectors of A transpose A, or vice versa. That's a little bit of a trick, because what we did was to go from the eigenvectors of A transpose to A transpose A, but it's the same in reverse. If you have the eigenvectors of you have a transpose X equals lambda X, then if I multiply, I have that. Then if I multiply on the left by A, I get A transpose A, X equals lambda AX. And then AX are the eigenvectors of A transpose. What we did was the other way around. We had started with the A transpose and multiplied on the left. A transpose Y equals lambda Y, and we multiplied on the left by A transpose. Right? But it's the same operation, just using A or A transpose to go from one to the other. Clear? All right. Convolution is commutative, linear. Linear in the second operand, in the second kernel, if you will. Likewise in the first, that's B and C. It turns multiplication, convolution to multiplication in both directions. So those are all true. The B-splines have continuity up to second derivative. And this said third, so it's not true that they're necessarily smooth in third derivative. But otherwise, yeah, the basis cubics for every patch are the same once they're centered at that patch. It has this nice locality property. So if you change something outside the aperture, it doesn't matter what happens with a particular patch. Okay, we haven't covered that D in this version of the course. That's not a question that would be on this exam for this version of the course. But you will see shortly, I think maybe in the very next lecture on Thursday, that there is a very nice algorithm for starting out with a coarse array and interpolating a finer array by a factor of 2 with a particular set of multipliers on the control points to get the new control points, and then doing the same to subdivide by another factor of 2, and so on and so forth, with the interesting result that the limit of that is the B-spline approximation. And so it turns out to be a much easier way to compute the B-spline approximation than the nasty thing that I showed you with all these polynomials and shifting around. And it converges very quickly, so you get approximately the B-spline approximation after only a few levels of subdivision. Yes, splines are applied separately, first in X and then in Y, and 3D and then in Z. So this is about using directional derivatives of Gaussians as match filters. But a match filter probably better described as a matched kernel, because it really isn't a filter. It's in the frequency, it's in the space domain, the matching. And its Fourier transform of that kernel is strictly the filter. But that's what people call it, so I've taught you that's what people call it, even though the name filter is misnamed. So Laplacian of the Gaussian is this Mexican hat operator. And it's circularly symmetric, so pretty nice for matching against circular blobs. To get a good match filter for edges, you should try to get the slope of the first derivative to be the slope of your edges in your image. The gradient is a vector, and its magnitude is the value of the direction in which you get the directional derivative result that's biggest. Sorry, its magnitude, yeah. And its direction is the direction for which that happens. Right? So that's a general property of the gradient of any function. Gradient of f as a vector has a magnitude and a direction. And this direction, u, is that direction such that d1u of f is as large as possible over all u's, over all directional derivatives. So it gives you the direction of maximization, and that particular u, for that particular u, d sub u of f is just square root of the sum of the squares of the derivatives. So it gives you a direct, for any function, the gradient gives you both the direction of where the directional derivative is strongest, which is orthogonal to one edge, and it gives you the value of the derivative in that direction. Okay. Okay, I taught many times what happens when you have an image with white noise, an image where there's correlated, where the intensity noise at 1 pixel is uncorrelated. You can think of it as independent. Oh, so it's a nicety in probability theory between things that are independent are uncorrelated, but not necessarily in the opposite direction. But fine, as long as they're uncorrelated, the RMS noise at any frequency is noise level is independent of the object width. But when you convolve with some other frequency, that the noise becomes colored. That is to say, you're multiplying the noise that has the same average level at every frequency by bigger numbers, let's say, for low frequencies than for high frequencies. So you end up with noise contributions that are different at different frequencies. And that's exactly not the white situation. You produce correlation, and indeed that correlation shows up when I talked about very briefly on the so-called character of the noise that you get when you apply an operator. The noise that looks salt and pepper ends up producing noise blobs. When we did our aliasing study, trying to understand how to choose the number of pixels, the spacing of the pixels, we understood convolution with a rect as producing the averaging over a pixel, but not multiplication by a rect. And then we understood the sampling as multiplication by a comb or a brush in 2D, or in 3D in this case. And so B, C, and D were all correct, as long as you understand that multiplication turns into convolution in the frequency domain, and convolution in the space domain turns into multiplication in the frequency domain. Anyway, and so you get that there was only convolution, there was only multiplication by a brush in the space domain. Not convolution. The others are so. If you have a Gaussian like this, it doesn't make sense to have sinusoids that are too big. They get canceled out by the Gaussian. It only makes sense to have ones that are that kind of thing. That is to say, where the wavelength of the sinusoids are order of magnitude or slightly smaller than the sigma of the Gaussian. Okay, so square symmetric matrices can always be written as a rotation, a diagonal. Once you rotate into sort of the eigendirections of the matrix, then you can do expansions in those three orthogonal eigendirections, and then rotate back. And R transpose is, because rotation matrices, their transpose is their inverse. They are matrices with all unit orthonormal rows, or because the transpose is their inverse, unit orthonormal columns. So A is true. You can still expand in terms of two rotations, but the rotations are not the inverses or the transposes of each other. In fact, they're not even in the same direct dimension if you have a non-square matrix. Whichever kind of a non-square. But it's not true that the rotation in one dimension is the same as the transpose in the other. Necessarily for a non-symmetric matrix. I will say that the way I performed this exam for this time around, there are way more true-false questions and way fewer multiple choice questions than in the other, but there's still some of each. We're getting to the end. Let me move along. This has to do with the h of x versus h of minus x. You need to understand that if you think about an impulse and the result of an operator on the impulse, that's the convolution kernel. But if you think about an output position as a weighted sum of surrounding, that's the reflection of. So if h of x is this blue thing, which happens to be non-symmetric about 0, then h of minus x is the red thing. And this is the impulse response function, and this is the corresponding weighting function for inputs for a given output. And of course, if h is symmetric, then its reflection about 0. That's what it means to be symmetric. Its reflection about 0 is the same. The main thing about 21 is to understand, first of all, that the FFT is just an algorithm for computing a DFT, for computing the sinusoidal coefficients. And therefore, it gives what DFT gives you, the coefficients of the basis sinusoidal images. And FFT inverse is the same algorithm with a minus sign in. couple of places as the FFT algorithm. So it doesn't take more time than FFT. It takes the same amount of time. Which is order n. Well, it's what computer scientists call theta of m log m, where m is the number of entries in the image. And you need to be careful because for us, for example, m might be in a two-dimensional image, m might be n squared, in which case you get n squared log 2 of n squared. But log 2 of n squared is is 2 log 2 of n. And theta says you don't concern with constant multipliers, and you don't concern with terms that have negligible effect as n gets very large. And therefore, we can say that this is order n squared log 2 of n. Okay. Almost done. I'm going to finish this, even though I'm running over. Okay, so okay, so the Laplacian is not that you need the kernel to be in the frequency domain to be the Fourier transform of the sum of all the second derivatives. Just the xx, the yy, and the zz is 3D. EFT is crummy for localization, but it does provide some information in the phase about local properties. It's not good enough. And but this Gaussian apertures is a good idea. And you can do this residue idea. Okay. Once you pixelize, you're stuck with the aliasing that you've done. You've incurred by that. You can't fix it with Gaussian convolution. This is the definition of folding frequency or Nyquist frequency. This makes sure you understand the difference between separable, which says you apply it in one dimension and then in the orthogonal dimension on the result, and isotropic, which says that the application is independent of any particular direction. I don't have any questions like this on this exam. It's all true, false, and multiple choice. Any questions about anything? Okay, we're done. I would love to see everybody get 100%. That's my favorite.